Hi everyone, my name is Jamila Bilalova. I'm 20 years old and I'm currently attending Wellesley College in Boston area in the US. And I'm focusing on both computer science and sociology. In the past, I attended Wolfram Summer School in 2018 and also Wolfram Summer Camp as a TA in 2018, 2019 and 2020. And I always highly recommend these two programs to anyone I meet. So today's talk is called Computational Farming, and it's something I became curious about in high school, and I didn't even know existed. So my talk will be more of like an introduction to this new field. So as you may know, our population is growing, which forces us to think about more innovation in sustainable and efficient farming. And one of the things that people are doing right now is trying to incorporate AI. And the fastest growing application of AI currently is called precision farming. Precision farming is kind of like an equivalent of computational farming, which relies on the collection, interpretation, analysis of diverse forms of digital data. And I really like this picture because it really shows how today our physical fields of crops are not just physical, but also digital, because they represent huge amounts of data. As you can see here, now we can both analyze a physical field and as well as like the digital field as we collect information. So let me go next. So precision farming, as I said, relies on the collection, interpretation, analysis of diverse forms of digital data, and it offers new ways for farmers to analyze their crops and make better management decisions in problems such as allocating labor or preparing storage, using water, fertilizers, pesticides. For example, precision farming can also provide tools that can, for example, track harvest yield and allow for the analysis of field variability, like differences in soil makeup, water, fungus. And variable rates technologies provide predictions and analysis so that farmers may customize the amount of input such as fertilizer or pesticide, on any portion of a field. And in my research, I am focusing more on smaller farms, like even orchards, because as you may know, bigger farms, they have more resources, so they have more opportunity to try new technologies, especially that are data-based. But smaller farms, they don't have the same advantage. So that's why in my research, I wanted to explore new technologies that can be applied on smaller farms. And one of them is called normalized difference vegetation index. It's this information you can get about your vegetation and use it to make better management decisions. So this is like the first example of what I see as computational farming in Wolfram language, is creating this NDVI function. So basically, healthy vegetation usually absorb and do not reflect red light. So like absorbs red light and strongly reflects near infrared light. And that's why this information can be used to apply false color gradient, for example, to images to better highlight the contrast between regions of healthy vegetation versus areas with like stressed or diseased or no vegetation. So this is just a pretty simple index, but it gives us a lot of information about vegetation that we have on our like orchards or farms. And NDVI in particular, as I said, it's like this dimensionless index that describes the difference between the visible and the near infrared reflectance of vegetation cover, and can be used to estimate the density of like green on an area of land. So it goes from 0 to 1 usually, and 1 indicates like a very healthy crop, and 0 is more like it's dead, and there's like in between. So this is something we can already use and get some information. So, but for that, we need to take it above the fields and take pictures. So the drone itself is just like a pretty cheap commercial drone, like compared to the ones that they usually use in like more advanced research. So this one had a single camera, which I modified. So I modified the camera to capture both near infrared and red light, because that's what we need to see if the vegetation is healthy or not. But I do it in the same image, however, in different color channels. So for the red light, I would try to make it go through the red channel, and the near infrared, I use it in the blue channel. I'll explain later how that works. And so this is like an affordable alternative to making a system that usually uses like two to three cameras or sensors that I've seen in like research done before. So I just wanted to make something that people can use in like on smaller farms that don't have enough resources to create these like very difficult systems. So yeah, for the camera, the first thing to do is to remove the infrared filter. That's like part of most cameras because we need that information. So remove the filter, and I bought this another filter that only allows red light. So as you can see, 660 nanometers. So red light passes through, and near infrared light also passes through, and the rest is like blocked. So the incorporation of this filter, it allows for the reflected red light to be captured in camera sensors red channel, and the near infrared light is going to be captured in the blue channel. And the green channel is just like not used at all. So this is how it looks. And we use the drone to take pictures of vegetation. For my like testing, I just did it on a piece of grass, which is not that fun, but I'm going to be explaining how I did it with the grass. And this is the post-processing in Mathematica. So this is the original photo. This grass, as you can see, was like more closer to fall, I guess, and some vegetation started to die. See, it's the near infrared, they would absorb it and like it would just burn it. So there's some parts that are healthy and others that are not. So we have the original picture, and then this one is with the filter that I just used that only allows red and near infrared light to go through. So the one issue that I had with this filter actually is that I had some optical aberrations, as you can see, like on the angles. Yeah, it's like not really correct. So I didn't know why that's happening, but the information in the middle was still okay. So I'm just like cropping here. I cropped the borders using image crop, just identify dimensions, and this is what we did. We have our final image that is cropped, and this is what we're gonna use to see which parts of vegetation are healthy and which are not. It's gonna be called crop sample. So yes, now we want to extract the two channels that have information that we need, the blue and the red. Red contains information about red light and blue about near infrared. So we use color separate on the crop sample, and we input blue and red channels. So we get these two images of just the blue channel and the red channel. And now we can use these two images to apply our NDVI function on. So NDVI function, as I said, equals the near infrared light minus red light over near infrared light plus red light. And we apply this function every single pixel of the two images. So this is our formula. And then when we apply on the blue channels, yes, it applies to every pixel, but at first we get this black image. So we need to just adjust the picture. We can't see any difference, but when we do image adjust, we can see now the difference. And as I said, the lighter colors will like indicate healthier vegetation. So like these parts should be like healthy pretty much. And then the darker it is, the more like stressed or diseased or even like completely dead parts of vegetation. Yeah, so this is like our final NDVI map, but also we can improve it a little bit better because we can't really see well. It's like black and white, not very useful. So we're gonna just do colorize it. We use colorize, we see it a little bit better. this time it's like the more blue it is, or like lighter, the worse the vegetation, and the more red, the more healthy it is. But also we can do conform images to conform the original photo and our NDVI map to get an even better representation of what's happening. So in conform images, it just like returns, uses a list of images and returns images of the same properties, like dimensions, just like adjusts to the same dimensions, data types, color space, and interleaving. And then we multiplied it two, and now we can see much clearly what is happening. Like the areas that are more red, they're more healthy, and the areas that are like blue or lighter, they're just like not as healthy. So this is one way to get some information about our vegetation on the farm, just by taking a picture using a simple filter. That filter cost maybe, I think, $70. So yeah, and this is the final function. Now in the map, we can apply it to any like original picture that was taken with the red filter. And yeah, so some applications, instead of just looking at a particular spot, we can try and like look at the whole farm and see which areas of the farm might be like stressed or having some issues, if you want to like have a bigger picture. This picture is from the internet. I didn't actually take that far away. So it's not the best one, but I think you get the idea. So you can use it on like bigger scale. Yeah, so this is how like the whole function works, and something small and useful. Yeah, there was another implementation. So after I told about this project at the summer camp, one of our students, Aaron Patel, he used the NDVI function, and he looked at compared the fertilizers on vegetation that like he was growing, and it showed that his novel fertilizer that he was testing was actually as effective as the current synthetic fertilizers, but also even outperforming its organic peers. So I think he used duckweed and he compared it to other fertilizers. And just by using NDVI, you could already get pretty good information about your vegetation. So, and yeah, and this is obviously like very exciting because it opens the door to like completely rethinking how we fertilize our crops, just based on this one index. And there's obviously many more indexes like this. You can look at nitrogen level, just like all sorts of information, but it's like the basic one. So another example of computational farming is trying to count the amount of like what we grow in our trees. It could be oranges, apples, whatever, because farmers actually really appreciate this information because they need to like see how many people they need to hire to collect their fruits and see how much storage they will need. And basically like it's usually pretty useful to know how much you have to collect at the end of your harvest. So yeah, the question is just how can we count all these oranges? Let me go. So yes, fruit detection counting. At first, I tried to see if anyone had like an algorithm to do this, if anyone did research in this area. And there was only really one group at UPenn who collected this huge data set of just like taking picture of trees, like making videos. And they collect information about where each like fruit is. I think here's like apples, here's oranges. And then they had information about like the X and Y of where the fruit is, and then also the radius. So it's like very detailed. But at first, and they used actually deep learning, but I didn't want to go right through deep learning. And at first I tried to just see if I can do it in Mathematica using the functions that they do have in here, which I think it's like a good idea to do before you jump into deep learning, because not every problem can be solved with just deep learning. And I know it's like very, like you just want to go to deep learning sometimes, but here I'm trying to see if I can do it with like regular functions that we have. Yeah, so at first I'm just like trying to see how this works. I binarize it. Well, this didn't look good at all. So I'm just using now like a value. Oh yeah, at first, yeah, it's just like separating the foreground, the background with a threshold. So I put it to 0.3, just something that worked for me better, but it can be like between 1 and 0. It creates this binary image that looks a little bit better than before. So you can see some fruits already not that overlapping. And then I just use select components and choose components that are based on like eccentricity and circularity, basically just how round it is. And I inputted 0.7, I think, yeah, and 0.8. Oh God, okay. Go 1 second. Yes, okay. So this worked, not too bad. I see now the fruit's a little bit better, but it removed a lot of the other ones. And so what we can do next is to use distance transform in order to like separate the overlapping apples, because there are some. And we do that by extracting like a set of markers by finding local maximas of the distance transform. And we use these markers later in watershed components. And after that, we will be able to count the apples. So distance transform, this is how it works basically. The value of each pixel of an image is going to be replaced by its distance to the nearest background pixel. So if you look at like a picture of like a horse, this is how it's going to be, the distance transform. So we do the same apply on our original picture, and we get this image. Let me see. Yes, so this is what we get. And then after that, we are finding areas in this like elevation map. Basically, it's right now it looks like an elevation map that rise above the surroundings, but like a certain threshold. And for me, I use 0.1. It can be anything you want, but I'm using 0.1. That looks better. So I'm creating a marker. You can see there's some more dots. And then after that, I'm using watershed components that uses like a binary image marker, this one, and to indicate regions where basins may be created. So we apply watershed components. This is what we get. We also colorize it. And now we can see, after we colorize it, each component is like a different color. And then we just use max, the function max, and we get 16. So this is like amount of apples, I guess, we have here, which might not be true, but it's at least something that we can get already using the functions. And if you want to play more with parameters and see which ones work better, if we combine all the functions together, we can use this like manipulate functions and see which parameters might work better if we change it. The distance, for example, we get a little bit less fruits. Maybe the min size is like, yeah, we can just play, see which one works better. But I think the one that I had before was like pretty ideal. Yeah. So yeah, this is how you can try and like calculate number of fruits on trees just by using functions in Mathematica. And the original approach was definitely deep learning, because as we could see by like trying just now, the old solution has some problems because there's always like illumination changes. There can be occlusions from foliage and neighboring fruits. There could be overlapping fruits. So in the end, it makes sense to go to deep learning because it's best with like dealing with unstructured environments. This is like approximately the algorithm you can use. So that's what the other group did. See, I think that's all. Yeah. So this is my like 2 examples of farming. Yeah, and I'll go check the chat if you have any questions. Let me know. Thank you. Yes, I will definitely share the notebook. I will add it in the end. Oh, so have you figured out how to map NDVI output to crop yield or some other valuable crop metrics? I didn't try, unfortunately, with other metrics. Um, yeah, but if you want, I can definitely get back to you. I also want to take a look at it. But I think there's definitely a possibility to do that. Um, are you planning to post the deep learning network into the Wolfram neural network repository? So that one is actually, it was, I don't have it right now. I tried to contact the researchers and they did, oh yeah, the papers. Actually, the paper is right here. It's called Counting Apples and Oranges with Deep Learning. It's a pretty good paper. Yeah, very fun to read. Yeah, and then I don't have the neural network to upload, and I didn't train it using Mathematica, which I think would be nice. But yeah, the other group, I think they used some other language, and like they never really shared it. But I'll try to work on that. Yeah, but at least the paper is here. Yeah, if you're like super interested, all the researchers that wrote this paper are pretty nice in like replying. So yeah. Oh yeah, yeah, yeah. Okay, I'm gonna try to see how I can access the participants. Allowed to talk? Does that work, Christian?
Yeah, can you hear me now?
Yes, I can hear you.
Thank you. First of all, thank you for your great presentation. So I have, my first question is, so I see that what you do here is basically post-processing of images, right? Do you see any use case of doing real-time processing of this data?
Real-time processing. Yeah, I think actually that's what they were trying to do, like their regional projects. So the pictures that I got in the data set are actually like extracted from videos. So what they try to do is to use the drone and just like make it fly right next to the trees and like make a video at the same time, so that it's like in real time tells you how much fruits you're getting. So you go by one tree, it says like, oh, like there's 15. You go by the next, it says, oh, now it's like 40. So that was like their regional idea, to be able to like walk around the field and take a video and just like see how many fruits you're getting. Yeah, I don't know if that's what you meant.
Yeah, like if you had Wolfram Language running on the drone, you could do that. Like you could process all that data while you fly the drone. And also, are you planning to add your NDVI function to the function repository?
Oh my god, yeah, yeah, I think I will definitely do that. I totally forgot. I'll add it and I'll talk to you if anything.
Okay.
Yeah.
Thank you very much.
Yeah, thank you. So, okay, I'm reading this other question. Have you got any links to papers or explored counting orchard trees from above? For example, satellite imaging. I mean, definitely, I used to read more papers on that. I'm not sure about satellite imaging. If I really focused on it, I try to like do more, try to read more research like around using drones. But even with using drones, I know it's like it can be super expensive, especially if you're like trying to create a new one and use a bunch of cameras on it, which is what mostly people did in the past. Um, but yeah, okay. I can try actually. I will go back like after the presentation and look at all like the folder with all the research I've read. I can put it in the chat. Hopefully it stays here. Just like a bunch of links that I've used, but I don't think I've looked that much at the into like satellite imaging. And I'll add the function. Thank you for sure. Oh, okay. Sorry, I just skipped one. How one get a close estimation of fruit counting in a tree as some may be hidden in leaves? Yeah, that's like the biggest problem for this one. So yeah, for me, it's like I just like played with parameters, but again, it's just like one picture, and ideally, I think in this case, deep learning may be better because in neural networks, like it's not just the information that you provide, like in the images that I have, but also what the neural network learned itself, like based on the 1,000 images it processed. So I think in this case, really like deep learning might be better at recognizing, but I haven't really like tried to go deeper into using the functions that we have to see if like I could estimate it a little better. For now, that's just what I have, these functions, but yeah, that's something I still think about. Okay, so what do you see as next steps in your research? So like ideally, I don't know if I wanted to continue this one in particular. Like it just took me a lot of time to like learn about this new field because it was so new. Like a lot of things that I was trying to do, it was only maybe like one other group on the internet that I found who tried to do something similar. And that's why like I try to like tell people about it more. And like one of the students at the summer camp who took this, at least like the idea of the NDI function, and did something that was interesting to him, that's like totally different. So I'm always like up for that. But for me, I think I would definitely want to look more into like the issues with pictures. For example, if you sometimes you take a picture and you have since you're relying on like how dark it is, like the map, how dark it is, sometimes you also get just what is it, the shadows? Yeah, like if you take it in the sun, you have the shadows, which confuses you. So like I still don't really know how to deal with like those type of issues, and I would love to take a look at that. And maybe just like talk to biologists more, to be honest. I'll just see how you can actually identify if like vegetation is healthy or not. Okay, I think I'm still here, right? Oh, it just like dropped for a second. Yeah, so deal more with like the actual images and see if there are any issues. Yeah, I don't actually want to jump into deep learning right now. I'd better stay and just like research more about like the actual leaves, or just like the vegetation, how to figure out that part. Let me also share it in the chat in NV. Yeah, I think I'm going to end here. And if you want, you can come back and try to get the NB. I'm going to upload it right now and also import some more research papers that I've read in the chat. So I'll try to do it fast. Let me close it right now. But thank you so much for attending. I really appreciate it. And you can always reach out to me. No problem at all. I have my email or just like on the Pathable itself. Yeah, you're very welcome. I'm glad to talk more about this. Thank you so much.